Howdy folks, welcome back to another CS 128 honors lesson. Today is lecture number 13. We're going to be continuing our discussion on parallelism and concurrency with these goals for today. So first, basically this lecture is split into two pieces. First, we will go over MP2. We will very briefly discuss MPSC again with some review. And then finally, we will do a big sort of, not even necessarily MPSC, but just multi-threaded example that I think is fun and cool and can start getting y'all excited for final projects a bit. Quick reminders, nothing is due that soon. Homework 9 is due on 3/11. Homework 10 we're releasing today. That'll be due after spring break. MP2 or 3 is also due after spring break. You do not have to work on homework 10 or MP3 during spring break. We give you extra time. Granted, you might want to work on it like this week if you want to get ahead, but we pretend like spring break does not exist for these. So you'll have the extra time. That being said, we do assign one thing over spring break, which is group forming and project ideation for the final projects. So during spring break, or by the end of spring break, we expect you to return with some idea of what you might want to work on for the Rust final project, as well as a group who you'd like to work on it with. So we really encourage you all. We'll be providing and helping form groups through the Discord, but reach out. Maybe we'll make a channel for y'all to introduce yourselves and talk about what you might be interested in working in. But start to brainstorm a little bit. On Thursday, our lecture will consist mostly of just continuing brainstorming, giving you all some cool packages, some cool ideas of final projects you might want to work with. And then also we'll very briefly discuss shared state concurrency. So instead of messaging, sharing memory. But that's for Thursday. Without further ado, we'll go ahead and get started. So quick, we had a quick question about borrowing. So there's still some confusion here, and I think that's completely understandable. I think way back when I said ownership is hard. This is why, right? Ownership as an idea I think isn't that complex, right? There's those three rules and they're pretty straightforward. But in terms of how ownership interacts with the code you write, it's borrowing, and borrowing is confusing. And so, this question is still a bit confused about borrowing. You get an error very often when you use it, and you have some specific sort of troubles when assigning changes to variables in the struct. So let me first answer this changes to variables in the struct question, because I think that's a little separate. So in this specific case, in the getWord function, we say, hey, you need to return self.word, and it needs to be lowercase, right? What the important thing that we wanted y'all to realize here is we don't have a mutable reference to self. And it wouldn't really make sense to have a mutable reference to self here, right? If we want to do something like return self dot, word, and then dot like two lowercase, this is going to edit self.word. Okay. And if it does edit self.word, word now depends on if this get word has been called or not, right? Which is, a little bit of a strange way of approaching it. Really what we want to do here is just pass a reference to self.word and don't edit it here. Rather, we need to edit it in new, or in guess, we also need to make sure the guess is lowercase, but the important thing is new, right? Before we even assign it as a variable in this hangman struct, we need to make sure it's lowercase. So, a little tricky there, but let's talk more generally about borrowing. The big idea that I want you to sort of keep in mind when we are borrowing is that, there's some piece of data, and currently someone owns it. And it depends what we want to do with that data, which is going to determine how we need to interact with it. If we need to, edit this data, and we need to make sure that nobody else is editing this data while we are, unless we say so, then we need to take ownership of it, okay? A second option is maybe we just need to look at this, right? We'll give it right back. We don't need to edit it. We just need to take a peek at it and give it right back. Then we just need a reference, right? I'll say ownership. We just need a reference. Okay, let's say, we just need to take this thing for a moment. We'll give it right back, but we do need to make some changes to it, right? That's a mutable reference, right? Okay, and so, in this example of like the getWord function, when we want to, just take a peek at the word, borrowing is hopefully, what you think of. Maybe, you say, okay, but we do need to edit this, right? We need to make sure it's lowercase. Well, your two solutions are either A, make sure it's lowercase to begin with by editing it in new, or, theoretically, you could have changed the function definition to take a mutable reference instead, and then changed it in place. And that would work, but okay, this goes back to the weird case of now self.word depends on whether or not the getWord function has been called, which maybe doesn't totally make sense, right? What we don't want to do is we don't want to take ownership of this, right? Because ownership sort of implies in a way that we won't necessarily give it back, right? Self.word. We're going to give word back to self, right? Self owns word, self being the hangman struct, word being, some string on the heap. When we call this getWord function, we just want to take a peek at this really quick, right? We don't want to take ownership of it because then we have to worry about giving ownership back and, lifetime stuff comes into play. It gets crazy, right? But okay, in the other hand, maybe there are situations where you want to trade. I mean, I think very, very often you want to give complete ownership of something or take complete ownership of something. And so I think when it comes to the confusion, you need to ask yourself, where am I getting this from? Are they going to need it? Do I need it? Do I want to give it back? And that's another big thing is if you want to eventually give it back, you're pretty much stuck to borrowing, right? Not necessarily. You can do some fancy ownership tricks. Okay, you can do stuff or some not so fancy ownership tricks of just like returning it later, but it gets weird and maybe not very efficient and also harder for you. Okay, so let's review MP2 together. Sorry for the jump cut there. My previous recording, I realized that I was not sharing my code the entire time. Okay, so let's sort of just go over some of these functions one at a time. So the MP2 new function, this is where we want to instantiate some new hangman game object. But first we need to check some cases. So let me do this. Okay, so the first case is if the word is empty. This one's relatively straightforward. We can just say something like word.length equals 0. If this is true, then we want to, return some error. Similarly, if the characters are alphabetic, there's a couple different approaches for this. You can do something like, iterating over word. So we can do like word.chars. Let me change this to say like for C in word.chars, if C or if not C dot is ASCII alphabetic, then return error, right? Something like that. And then finally, we want to return this hangman struct. Okay, and the hangman struct depends a lot on what yours looks like, but at the end of the day, you say like let x, which is a hangman type, equal hangman, instantiating some struct, and okay, you set word to be like word dot to lowercase. We discussed, it should be to lowercase because the get word eventually, and then, any other things that you need to set here. I kind of generalize it because you're free to change the struct for this MP, and we really encourage you to. I mean, our sort of implementation was fine, but there's, I think, more efficient ways to do it for sure. The hash set's pretty good though. I think that was a good one to keep. Okay. So let's discuss some of the other ones. So this get word function is relatively simple. I think really the big idea here is just, we just need to return some reference to self.word, and we can't really edit that reference here, so that should be fine. Get number of guesses left is basically the same thing. There's a little bit more complexity, meaning, okay, we have some total number of guesses that the person has, which I think was num guesses total. And we want to return that basically minus the number of incorrect guesses, right? So something like this should be totally fine. I wonder if it's worth it to like fade this in and out every time. Maybe. Okay, so number of correct and incorrect guesses, or get correct and get incorrect guesses, was also relatively straightforward. This one is just returning a reference to, self.correct guesses should have been fine. Yep, that returns a reference to a hash set, so that should be good to go. Okay, now we start to get to some of the longer ones. So first we have this get game result function, right? And this get game result function has a couple different options in it. So first we get a reference to self, we return an option of a Boolean. We want to return some true if they won the game, if the game is over and we have won, some false if the game is over and we have lost, and then none if the game's not over yet. Okay, so let's fade this back in and let's check those cases. So what's the first case? So if we have won the game, then we want to return some true, right? So I'll smack this in here. Okay, and what is our if statement here? So if, okay, so if the number of correct answers that they have is equal to the length of the word, then we're good, right? So that's one way to do it. But this is sort of one of those cases where you can do it a couple different ways. Obviously, we can't quite do if self.correct guesses.length equals self.word.length. Okay, and why doesn't this work? Okay, if your word is something like crate, which is my Wordle starting word, then this would work, right? Because our set would contain C-R-A-T-E. But if you were not as good as Wordle as me and you played a word like onion, our set actually only contains O and I, right? And so the length of this is 5, but the length of this is 3. And so even though they guessed this correctly, their game should be over, it wouldn't be because of repeated letters. So, okay, there's lots of different ways to do this. I recommend somewhere in your guess function just keeping track of how many letters the person got correct, and then basically just comparing those two things here. So like if self dot correct guesses, or, or I guess that's already used. If self dot number of correct positions, we'll say, right? But we also need to make sure that they haven't already lost. So and num guesses total is less than self dot number of, or we can just, in this case, we can just say incorrect guesses dot length, right? Okay, so that one's good. We also want to check if the game is over. This is relatively straightforward. It's just the same case here, right? So if num guesses total is greater than or equal to, then we want to return some false. And then otherwise, return none. Okay, hopefully this made sense. I think this is where sort of your creativity on how you make this struct comes into play, because this function can be sort of extremely difficult or extremely easy. If you keep track in sort of guess or something of the number of correct positions, I think that this is very easy. Otherwise, you basically need to say like let a equal, some, we'll just say 0 for now, and like, okay, iterate over correct guesses, iterate over correct word, count matches, and basically find this out every time, which again isn't the end of the world. That's another way to approach it, but just some thoughts there. Okay. And then finally the big one, okay, the guess function. So this is a huge wall of text, but let's try to break this up into a couple different pieces. Okay, so first, let's handle our edge cases. So first edge cases, you should use a game already over error kind if the game already finished before the guess. Okay, so this one is relatively straightforward. We'll fade the code back in. Okay, we luckily have this self.get game result, and if it is some, right, if it's true or false, then the game's already over, and we can return, error of hangman, error of new, of hangman, dot, 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 basically game already over. I'll TLDR it. Great, okay, so that's one edge case. What's the next one? An invalid character if the character is not alphabetic. Okay, this one is also pretty easy. So we can say if C is not ASCII alphabetic, then return invalid character. And the next edge case is the already guessed if we already guessed it. Okay, so this one, okay, I think the big sort of task here is just finding the dot contains function for the hash sets. So we can say if self dot correct guesses contains, oops, our character, or self dot incorrect guesses contains our character. Then, okay, return already guessed. Now there's one case you have to keep in mind, which is this character could already be uppercase, so it's probably smart to turn it into lowercase before we do this check, right? Because everything in this self.correct and incorrect guesses should probably be lowercase. And so, okay, maybe we just say like let x equals c dot to ASCII lowercase. Wonderful. Okay, and that's actually all of our edge cases. So now we can eliminate basically all of that text, which is very nice. And all we have now is, okay, we should return okay true if the guess was valid and correct. We know it's valid now. And okay false if the guess was valid and incorrect. So now we just need to see if it is incorrect or correct. So again, lots of different ways to do this. I think okay, yeah. So our approach for this was a little bit weird, but at the end of the day, it depends how you're storing this string and how you're storing the correct sort of things. Um, but at the end of the day, it's check if character is in the string. If yes, then we need to, okay, add this to correct guesses. Keep track of the number of correct positions, potentially, unless you want to do that in your other function that we were looking at, that is game over. If it is not in the string, then add to incorrect guesses, and also increment number of incorrect guesses. Now, this depends a little bit on how you did this get num guesses left function. If you just add it to the incorrect guesses and you use the incorrect guesses dot length, then okay, this isn't even necessary. But there's some situations where, I saw a lot of you were sort of keeping track of these separately, but forgot to always sort of increment. Okay, some edge cases there. But that's pretty much it. Okay, I know it was a little pseudocodey. Let me know if y'all like this style or didn't like this style. But in either case, let's get started with the cool part of today's lesson. Um, with just some ideas of MPSC first. So let me move things around on my machine very quickly. That was me, not you, don't worry. Okay, so we want to remember this idea of message passing, right? We have one consumer and potentially many producers, right? And when we create a channel, basically all we're saying is, okay, let me start listening and send some information over, right? If you're curious on, how this is actually implemented, it's just really a queue, a queue, and you put some information in, some message that you'd like to send to the receiver, and other threads are putting their information in, and then the receiver is sort of popping each of these elements out and processing them, right? That's pretty much it. There is some extra complexity that needs to happen here. So funny enough, like this is shared memory, really fundamentally, right? And so, these have some mutexes and things, locks that prevent multiple threads from putting basically the same piece of data in the same location and one getting overwritten. But that's all abstracted away. You don't actually have to worry about that unless you want to build one of these yourself, which you absolutely could. And honestly, it would probably be faster than Rust's built-in implementation. But okay, if any of you are interested in doing that, I'll let you explore why Rust's implementation is slow. Okay, so for this example, those of you who are more sort of mathematically minded, this will be fun. I think you'll really enjoy this. For those of you who aren't, this doesn't require too much complex math, so don't worry. But imagine we just have some point, okay, on the complex plane. So we have imaginary and we have real. Really, just imagine these as like two different dimensions. It doesn't even matter that these are imaginary, but we have 1, 1, or we have -1, -1, or some other random point. We want to ask the question, for what values, for which of these points will this formula eventually, approach infinity, right? And okay, let's really quickly analyze this formula. So the next iteration is equal to the past iteration plus some constant value. So let's start with 0, 0, for example. We do 0, 0 squared, which, okay, this is where my imaginary number math is going to fall apart, but I believe it's a squared minus b squared is the real part, and then the imaginary part is 2ab. I'm not going to solve this every time. And then let's say c is just like 1, 1. Okay, so the next iteration becomes 1, 1, because this will remain 0, 0. And then the next iteration is 1, 1, and we square this, and I don't know what it becomes. Okay, maybe I do know what it becomes. It becomes 0, 2, and then we add 1, 1. And so now it's 1, 3. And now it becomes negative 8. This is tough. Slow math. Okay, negative 8, 6, and we add 1, 1, and it becomes negative 7, 7. And if we do this again and again, will this eventually explode? Okay, so for this specific example, the answer is yes, clearly. I mean, this is exploding. But more generally, for what values of c does this explode? Does this explode for all values of z? And the answer to those is actually generally, no. So there's a lot of complexity that's involved here. We're going to be finding what's called a Julia set. So we're answering the question, for what values of, or given a specific c, for what values of z does it explode, what values of z does it not explode, and things like this, right? So we're essentially looking at okay, if we take this point, we're trying to look at where it eventually ends up, and then depending on where it eventually ends up, we'll color this point a specific color. Okay, for some c. And then using that same c, we'll find it for this point, for this point, for this point, for this point, etc., etc. Okay, there's another version of this called the Mandelbrot set, which changes this around. And it says, okay, for z is always equal to 0, 0, for what values of c does this explode? So we can see for z is equal to 0, 0, this value of c, it will approach, I think this is infinity. Maybe it's the other way around. This might approach 0. I think it's the other way around. Yeah, this should approach 0. And like this point will approach 0, but like this point approaches infinity. Okay, and we can look at a little bit higher resolution version of this, as well as a slightly different formula, and we can see, it's a highly, highly complex structure. It's a fractal. You can zoom into infinity, all this other fun stuff, right? Okay, and so let's analyze how we can actually code this. So let's move over to here. Oh, but first, the first step when we want to do this is, in the spirit of final projects, we're just going to Google. So I Googled Rust Julia set, and I found this GitHub, which is the same one over here, and this is the person's code. And so I used this code. And this is what we're going to be basing our code off of. I've made some slight adjustments to it, which we can see here. Okay, so some slight adjustments. I reduced the resolution a little bit. I implemented complex numbers instead, just because it makes the math a little bit cleaner. And that's pretty much it. Okay. And so let's just really quickly analyze what this does. We want some image, and we want for each pixel to calculate if this eventually explodes or not, right? We'll go for a maximum of 200 iterations, and if it doesn't explode by then, we're going to say that it's never going to explode. For each pixel, we will first, okay, kind of converting the resolution dimensions into image coordinates. Don't worry too much about this. The important part is, okay, we have this complex number, which begins with the, complex coordinates that we want, the real and imaginary. Then we will square it and add c again and again until it explodes. Now, we know, this is a little shortcut, if the norm ever becomes, so if the distance ever becomes more than 2, it will continue sort of growing into infinity. And so we can stop early if that occurs. Okay, and then finally we just do like some hacky math to convert this into RGB colors. This is actually the original person's code. It works well, so I just didn't touch it. And we place a pixel of this specific RGB value in that location. Okay, wonderful. So let's run this. Okay, this is currently main.rs. I'll make sure it's saved, and we'll do cargo run. Oh, and I also added a little timing here. Wonderful. Okay, so we're compiling, and it takes about 4 seconds to generate this image, and this is what it looks like. So super, super cool. At least I think it's cool. But okay, it took a while, right? And especially, with images like this, I mean, I don't know about you, but I want some higher resolution. And so let's bump this up. Let's bump this up to something like 8,000 by 8,000, right? Maybe that's a little too far. Let's start with 4,000 by 4,000. So the issue is, this is taking a really long time. And currently this is single threaded, and that's totally fine. But we can make this multi-threaded, and, things will probably necessarily be better. Is this done yet? Okay, that's still running. And so let's analyze a little bit on how we can actually make this multi-threaded. Okay, give me one moment. I'll save here. We're going to be using the Rust thread pool crate. And so the first step is sort of just to install this crate and get it into our package. So all you have to do to install this crate is, okay, we'll copy this right here. And we will go. Oh, this finished. Okay, so 4,000 by 4,000 took, let's see, how long does that say? 21 seconds. And it looks pretty cool. Granted, okay, it's a little smush now, but, still this isn't quite as high resolution as we want. Okay, so let's now add thread pool to our crate, which is as simple as just adding thread pool like this. And let's edit our code. Okay, so first thing we're going to need to do is import some of the stuff that we want. So we'll use thread pool. Oops, that should be a capital P. And we'll use std sync mpsc. Okay, and this thread pool allows us to just sort of spawn up a ton of threads that are waiting for tasks. And then we can assign tasks to them. And whenever they're done, they'll work on some new task, which is super nice. Lots of awesome packages that allow us to do stuff like this. So let's just say let pool equal thread pool new. And we'll say n workers. And okay, my PC I think has 8 cores. And so we're going to say let n workers equal 8. Though maybe 16 would also be fine. And let's also create a communication channel. txrx equal mpsc channel. Okay, and now let's simply start to make some adjustments here. So we know let's say each thread does 1 pixel for now. Okay, and so first thing we're going to need to do is clone the transmitter. txtemp equal tx.clone. And we will execute. So this is just from the documentation for pool. This is in the way. Apologies for the thing being in the way. Maybe you could see, maybe not. Okay, all we did is import. We created a pool, and now we have cloned our transmitter, and we want to execute. So clone.execute. Whoops, pool. And just like our normal thread spawn, we give it a closure, and this closure is the code that we would like it to execute. And we will execute everything here. But instead of putting the pixel on, we will send it. So tx.send. We'll just send xy pixel. We'll just unwrap it. Okay, and we comment this out. Okay, and this really works. The only other thing is, okay, we can safely add a move keyword here, or else it'll yell at us. And that's it. We also need to build our receiver. So how many messages are we going to receive? 1 for every pixel. So width times height. We will collect x, y, and pixel into rx.receive. So this is another way of receiving. We can just wait for a message to come through, and we will unwrap it. And then we will put the pixel, just like this, in the correct location. Okay, so for each pixel, we spawn a thread to calculate that pixel. That thread sends a message back. We place that pixel in the correct location, and then we finish. Wonderful. So it was really sort of that easy. Let's start with just one worker for now, and just to benchmark some different times. So we'll cargo run. We have a quick error. Okay, so I see that we're using tx instead of tx temp here. So I'll fix that. Local variable exists with the same name, tx temp. Are we using tx in a different location? I wonder. I type it. I was a little confused what was happening there. I didn't add an E. Okay. So this is running. Still on the 4000 by 4000, which maybe I should have reduced. But okay, currently, technically, this is still single-threaded, right? Technically, this is like a really inefficient way of doing this. But for reference, the previous approach took 21 seconds. For the approach that every single time we want to do a pixel, we spawn up a single thread to do that pixel, or rather we have one thread running and we give it a task for single pixel, it will take, okay, probably a long time. We'll wait just a moment. Okay, 35 seconds. So much, much longer, right? This is because at the end of the day, this communication step is expensive, right? And so it's adding a lot of time. So I'm just going to not let that write an image, and I'll cargo run again. This time, we're going to use 16 threads. We run again. So effectively, the same thing is happening. We're assigning all of these tasks, and then once these threads finish, they are picking up that task and executing it, and then moving on to the next task. And now it only takes 17 seconds. Okay, so a little bit of an improvement, but okay, I ask you a question, which is, we just saw that it's expensive to create these threads and to send these tasks. So what if we just have each thread do multiple things? So we'll have a thread do an entire column. All we have to do is move this for loop inside, and let's run it again. Okay, so we were at 20 seconds for the single thread, 35 for the, I guess, single thread with many tasks. And just by making this change, we're able to bring it all the way back down to 5 seconds, which is amazing, right? 400 times faster than the single threaded approach, which is really nice to see. Of course, this could go even further. We can maybe, tuning and workers, changing iterations, changing the resolution to be what we want are all sort of viable options to make this work how we expect it to. But okay, I just hope that this example, A, isn't too confusing. Okay, maybe the math itself is sort of complex, but how easy it was to convert some single-threaded program to a safe and 400 times faster multi-threaded approach. Okay, and these thread pool and MPSC are just one approach. There's a ton of really awesome packages that we'll be talking about in the future that can help you make things parallel. And I hope that this all at the end of the day just makes sense. Anyway, let's end today's lecture by just looking at some fun graphics. I'm going to fix the resolution a little bit because I think that it's really distorted, and I'll change this like 0.29 for fun, just so we get a little bit of a different image. Okay, and it's writing the file. Interestingly, writing this image actually takes much longer than you would expect. I think because it has to convert it all into like PNG. Wow, holy cow, I haven't tried this one before. Okay, really pretty. 2.9 was a good choice. Look at that, huh? Okay. Anyway, I hope that you all enjoyed this today's lesson. Once again, start brainstorming some cool ideas for projects. See you around. Bye-bye.